Moving into section 6.2, we're going to start solving equations using trig functions, inverse functions, specifically linear methods. Now, if I remember correctly, this is one of the topics that I do not do quite the same as the My Math Lab videos and helps. So what we do in this video may be a little different than the homework help instructions that you get. That doesn't make me wrong or them wrong. It's just an alternate way to do it. Now, as I'm solving trig equations using linear methods, basically it means that I'm approaching it from, think about it, algebraic standpoint. There's some things that you need to keep in mind. Remember that if you have a quadratic equation, that means you have a squared term, and you want to solve that by factoring, by doing reverse FOIL. But if it's not factorable, we need to remember the quadratic formula. So I'm going to get that out there just so that you have it in case you've forgotten. The quadratic formula is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Remember that some other information that it's going to be good to keep in mind is the periodicity of our functions. When we were graphing our 6 trig functions, remember that our major functions, sine, cosine, and their reciprocals had a period of 2 pi, and then I divided that by b when I did a transformation. While tangent and cotangent, so sine, cosine, cosecant, and secant are all periodic over 2 pi, while tangent and cotangent are periodic just over pi. So my function, the period for this function, it repeats more frequently on a standard function rather than the other 4. Okay, here is my recommendation to you. As I'm solving trig equations, we start with what we get solving our inverse functions. So we start with that limited set of values, but then I want to think about what values are possible. No matter what it says, typically, I'm going to find all solutions first because my function, if I don't limit it to just those two quadrants, continues forever. It's repetitive. My angles are angles of rotation. They can just keep getting larger, either positive or negative. So think about finding all solutions first. That's where this periodicity comes into play. And then narrow it down to the window that you are asked to look at. So for example, this first equation we're asked to solve says to solve for all the solutions over the interval 0 to 360 degrees, and then to solve for all solutions. Well, we're going to go the other order. We're going to start by finding my entire solution set, all possible solutions. And then we're going to look to see which solutions fall within this limited interval. Okay, so we are solving 3 tangent theta minus square root 3 equals 0. And we're going to start by solving it for all solutions. 3 tangent theta minus square root 3 equals 0. Think algebraically, this tangent theta is my unknown. It's just x. This isn't quadratic. This is just linear if you want to think in those terms. So I'm going to move square root of 3 over. So I have 3 tangent theta equals square root 3. And then divide both sides by 3 to finish solving. So tangent theta equals square root 3 over 3. That is my solution. I want to know for what angles theta is that true? For what angles? And remember it says we are in degrees. And we know that for sure because our interval is 0 to 360 degrees. So for what angles in degrees is my tangent function value square root 3 over 3? Well, remember that tangent has a period of pi. So I don't need to list every single angle whose tangent function value is square root 3 over the unit circle. I just have to figure out where the first one is. If I look in quadrant 1, because tangent is positive in quadrant 1, 30 degrees has a tangent function value of square root 3 over 3 because tangent is sine over cosine. And if I simplify that, if I set it up 1/2 over square root 3 over 2 and simplify, I get square root 3 over 3. So my starting point is 30 degrees. If I rotate 180 degrees down here to 210. 7 pi 6, 210 also has a positive tangent function value, square root 3 over 3. If I keep rotating every time I land at my reference angle 30 degrees back around here, I have another angle whose tangent function value is square root 3 over 3. So here's how I write that, all solutions. I'm going to say, fancy brackets, 30 degrees plus 180 degrees in, where n is any integer. So any positive or negative rotation of 180 degrees from 30, I have another angle whose trig function value is square root 3 over 3. This is my all solutions. Okay, now let's think about over just this interval, 0 to 360 degrees. Well, that's just one rotation around my unit circle. We already said 30 degrees. If I go 180 degree rotation, I'm at 210. If I go again, I've wrapped back around and I would be at 390, and I've moved outside of my interval. If I want to look at that methodically, I would say, okay, so within my interval, I've got 30 degrees. That's my first, where n equals 0. I've got 30 degrees. N being this n right there, where n equals 0, I've got 30 degrees. Where n equals 1, it would be 30 plus 180, would be 210. If I did n equals 2, that would be 30 plus 360, which is 390, and I've moved outside my interval. So these are the only two angles within the interval 0 to 360 that fit the solution to that equation. All right, let's do another. This is another linear function, linear trig function. I need to solve for theta, and I'm going to do all solutions first and then come back and look at just the solutions within that interval 0 to 360 degrees. So I've got my equation 2 sine theta plus 1 equals 0, and I need to solve for sine theta. Well, when I solve for sine theta, I subtract 1 from both sides and then divide by 2. So I'm looking for angles whose sine function value is negative 1/2. Now remember, sine is periodic over 2 pi. So where is sine negative? Negative 1/2. Sine is negative in quadrant 4 is where we find our, if we were going to use our calculator, we would return an angle in quadrant 4. Sine is negative 1/2 here, and we're in degrees, so 330 degrees. Sine is also negative over here in quadrant 3. We've got a sine function value of negative 1/2 here at 210, that 30 degree reference angle again, but we're in quadrants just 3 and 4 because we're interested only where sine is negative. If I were to sketch that just so I can see a picture of it, I see I've got this 30 degree reference angle right there. So we're going to say that is 330 degrees. And then I've got this 30 degree reference angle right there. We said that one is 210 degrees. And then any number of rotations. I can rotate around as many times as I want. Now with tangent, because tangent is periodic just over pi, when I went to this 30 degree reference angle here, that 30 degrees has that tangent function value I was looking for. And we said that 210 also had that tangent function value I was looking for. I saw that I could get to all of these by rotating 180 degrees each time. And I could just keep rotating 180, 180, 180 in either direction, clockwise or counterclockwise. And I would end up at the angle that gave me the function value I wanted. However, sine is periodic over 2 pi, which means that to land here, if I start at 330, to land here again, I have to go a full rotation to get back there. This is a weird, not steady value. See, I would have to add 240, and then I'd add less than 180, and then I'd add more, so that doesn't work. So I have to do one starting point here, and then every rotation. And then I also have to do one starting point at this location at 210 degrees, and then every rotation from it. So whereas for A, I was able to write a single statement, a single starting point, and then rotations of 180 in. For the second one, I have to recognize that, okay, I'm going to start at 210 degrees plus a full rotation 360 in. Or I can start at 330 degrees plus that rotation 360 n, where n is any integer, positive or negative integer, and that gets me my all solutions. But I have to list both of those starting places because it's sine and it's periodic over 2 pi. Now I'm going to come back around and I'm going to look to see which angles fall within that interval, where my interval is just one way around the unit circle. So it's just these two initial values. If I start where n equals 0, I've got 210 degrees and I've got 330 degrees. If I went to n equals 1, that means I'm adding 360 to each of those. That would put me at 570 and at 590, and both of those are outside my interval. So these are the only two angles within that interval that I'm interested in. So my answer to A is just 210 degrees, 330 degrees. All right, let's look at another type of equation. We're still doing the same things. We're just looking at different types of equations to solve as we do it. Now this time we're going to be factoring. Our equation that I'm given to solve is cosine theta cotangent theta equals negative cosine theta, and I'm solving it over this interval. Now it does not ask me for all solutions. We're going to go ahead and talk about all solutions, but it doesn't ask me for it. Okay, so I've got my equation. Cosine cotangent of theta equals negative cosine theta. I'm going to set it equal to 0 because that tends to make things a little easier to solve. So cosine theta cotangent theta plus cosine theta when I move that term across my equal sign. And then I see that I have a common factor. So I've got cosine theta times cotangent theta plus 1. I've factored out that common factor. Now I have cosine theta times this binomial factor. My zero factor property, think back to college algebra, my zero factor property says I can set each of these equal to 0, because if a product is equal to 0, that means one of my factors has to be 0. And I get two different solution sets. I get the solution set that is going to make this equation true, where cosine theta is equal to 0. And I get another solution set that makes this equation true, where cotangent theta is equal to negative 1. Those are going to be my starting places. So let's think about where this happens. Where is cosine theta equal to 0? Well, cosine theta is equal to 0 at the poles, right? So we've got at 90 degrees and at 270 degrees, cosine theta is equal to 0. And each time we rotate back, we've got another cosine theta value of 0, positive or negative. Now, cosine is periodic over 2 pi, but this is kind of a special case because we're on the quadrantals. So I could do 90 plus 360 and 270 plus 360, but since they're quadrantal angles, I can just say 90 plus 180n, and that's going to get every possible rotation in either direction. So for all solutions, which we weren't asked for, but remember that I told you we were going to consider, we've got 90 degrees plus 180 degrees in from here, because we could have done 90 plus 360 and then 270 plus 360, but that's more wordy than it has to be. I can simplify it to just 90 degrees plus every rotation of 180 in a positive or a negative direction. That's going to give me every angle to infinity where the cosine function value is 0. All right, let's look at cotangent theta equals negative 1. Well, where is cotangent negative 1? Cotangent is negative in quadrants 2 and 4. And it's going to be a negative 1 at those 45-degree reference angles in those two quadrants. Notice again, cotangent is periodic over pi. Those are directly opposite each other. So we can just do a single starting point and then rotate from there. So at 135 degrees, I have cotangent negative 1. And then down here, if I rotate another 180 degrees past that, I'm at 315. Cotangent is negative 1. And I can just keep doing that rotation and find another angle that satisfies that, that requirement. So I can write that starting statement as 135 degrees plus 180 degrees in. And then I have to define where n is any integer. So that is all solutions. That's my all solution statement. Wasn't asked for it, but that's okay. I was asked for this interval from 0 to 360. Well, from this factor, I get the 90 and 270. From this factor, I get 135 and 315. So those are the 4 angles within that interval 0 to 360. If I was allowed to keep going, I would have more. But these are the 4 within that interval. All right, let's look at the next one. We usually skip this one in class for the sake of time, so we're going to kind of talk through it quickly. It's exactly the same style of question. I'm going to move that sine theta over so that I have sine theta tangent theta minus sine theta equals 0. Factor out the common factor so that I get sine theta equals 0 and tangent theta equals 1 as my solution set. Well, I know that sine theta is 0 at 0 degrees and 180 degrees. I know that tangent is 1 at 45 degrees and 225 degrees. So that is my solution set within the interval. If I do an all solution statement, even though sine theta is periodic over 2 pi, this is a special case again because these are quadrantal angles. So I can say 0 plus 180n, as well as 45 degrees plus 180n, where n is any integer. And we haven't learned any new methods for solving. We are just solving just like we did in college algebra. Okay, let's look at our next example, example 3. Now we see a squared term. So now we're going to use our quadratic methods to solve. Remember, we're solving for all solutions and then finding the solutions within the interval. You're welcome to use our substitution method for solving. In college algebra, we taught it as AU squared plus BU plus C equals 0, where you substituted in U for whatever that base variable was. In this case, you would substitute in U for sine x. It just makes it a little easier to look at. I usually don't mess with that. I usually go ahead and just factor it as it is. You're welcome to do whichever way makes you the most comfortable. But we have 3 sine square x minus sine x minus 2 equals 0. This is quadratic. We're asked to solve for the interval 0 to 2 pi, so I know I'm interested in solutions written as radian values. I'm still going to start by solving for all solutions. I'm going to solve for all solutions first. It's easier for me, that's solutions there. It's easier for me to look at it that way, and I make sure I don't leave anything out that way. Okay, so I'm going to factor this. This is factorable as a quadratic. 3 sine x and sine x are going to be my first terms. 2 and 1 with sine, the algebraic signs are going to be different. 1 plus, 1 minus. I don't want to multiply 3 times 2 because that would be 6. It wouldn't allow me to get this negative 1 in the middle. So I know I need the 2 there and the 1 here. I need 3 times negative 1 to get me negative 3 sine x, and then a positive 2 sine x, so that when I add those outside and inside products, I get a negative sine x as that middle term. Reverse FOIL. If you need to review FOIL, go back and look up some Khan Academy videos about how to FOIL and how to factor quadratics using reverse FOIL. That would be a really good refresher at this point if you're confused with the factoring. Now, zero factor property says that if I multiply 2 factors together and the result is 0, then that means at least one of them has to be equal to 0. So I see what would make that happen by setting each of my binomial factors equal to 0. When I solve for sine x in this first factor, I get a negative 2/3. When I solve for sine x in the second factor, I get a positive 1. Now 1 is a sine function value that shows up on my unit circle. When I look at my unit circle, sine is positive up here, and it's a positive 1 at the pi half. So every time I rotate around to pi half, I get another value, sine function value of positive 1. So 1 pi half, 3 pi half, back around to 5 pi half, or I could go the other way and do start here and do negative pi half. But it's going to be always landing here on the circle. So I've got a rotation of 360 degrees to get back here. It doesn't work down here because that's a negative 1 as my sine function value. So for all solutions, for this, I have pi half plus 360 because we're in radians, excuse me, plus 2 pi n. Every pi half plus 2 pi n is going to give me my all solutions to get this sine function value of 1. So that's my first place that satisfies this equation. My other one, sine x equals a negative 2/3. Well, negative 2/3 is not a special angle on my unit circle. I do not have a sine function value for a special angle on my unit circle that is negative 2/3. So we have to think about sketching our angle and using our calculator and doing our inverse sine function. Now I know that when I use my calculator, I'm going to get an angle because sine is negative. It's restricted to, sine inverse is restricted to quadrants 4 and 1. Sine is going to be negative in quadrant 4. Now I know that sine is also negative in quadrant 3. I'm going to have to figure out what that value is going to be though. My calculator won't give it to me. Let's look at our calculator and see what we get. All right, I'm in degree mode. I need to switch to radian mode. And once I'm in radian mode, I'm going to say sine inverse of, and it's a negative 2/3. And that gives me a radian value of negative 0.7297. And that's what I'm going to use, negative 0.7297. So I've got negative 0.7297. That's how far I am away from, so that is my reference from the x-axis is 0.7297. So what is this value going to be over here? Well, this is pi, and then I have to go this much further. So I'm going to take that, and I'm going to say, all right, I'm going to multiply that times a negative 1 to get it to a positive value because I need to add that to pi. So that value plus pi tells me that this angle over here in quadrant 3 is going to be 3.8713. So this is 3.8713 radians. So I have 3 starting places for my all solutions. I have pi half plus 2 pi n. I have a negative 0.729787. Let me do that again. Sine inverse of negative 2/3 is 97 plus 2 pi n. And then my third starting place is this one that lands over here, 3.8713 plus 2 pi n. Okay, so that is all solutions where n is any integer. Now, if I were interested in all solutions, I could just keep rotating and I have an infinite number of angles that land at those 3 locations. Sine x is 1 here, so that's that solution at pi half, and sine x is negative 2/3 at these 2 other solutions. So those are the 3 locations on my circle where I'm going to find angles who satisfy this equation. Which of these are within my interval that I'm actually interested in naming, 0 to 2 pi? Well, pi half is. So where n equals 0, I've got pi half. I've got negative 0.7297, and I've got 3.8713. Out of these 3 solutions, this one and this one are inside my interval 0 to 2 pi. What if I go to n equals 1? Well, if n equals 1, I'm adding 2 pi to each of these values. So I've got pi half plus 2 pi would be 5 pi halves. That's outside my interval. If I start here and I go a full rotation, I've just moved beyond 0 to 2 pi. So that's outside my interval. I definitely don't need to go any further. Now I'm going to do this, and I'm going to add 2 pi. So let's start there. Let's do negative 0.7297, negative 0.7297 plus 2 pi. and I'm at 5.5535. 5.5535. That's within my interval. This wasn't. That was negative. That's outside my interval. This is inside my interval. If I start at 3.8 and I add 2 pi, 3.8713 plus 2 pi, well, that's definitely beyond 2 pi. 2 pi is about 6.28. That is definitely outside my interval. 2.1545, outside my interval. So these are the 3 angle values that are inside the interval that I was asked to consider. So I've got pi half, I have 5.5535, and I have 3.8713. I'm sorry I didn't put those in order from least to greatest. So I've got all solutions, which is, I wasn't actually asked for that, but it's good to find. And then I have these 3 angles that fit within my interval. Let's do another like this. We've got another quadratic. This one, again, is factorable. So when I factor this out, I get tangent x. I need a +2 and a -1 in order to get to this -2 at the end and a positive tangent x in the middle. I set each of these equal to 0 and solve. So I get tangent x is tangent x is +1 and tangent x is -2. Well, tangent can be anything. There are no restrictions on my tangent function values. Let's see what that happens. Well, where's tangent 1? Tangent 1 is 1 at the angle pi fourth, and then tangent is periodic over pi. So every pi in after that, I have another tangent function value of a +1. -2 is not on my, it's not a special angle on my unit circle, so I'm going to use tangent inverse on my calculator. So tangent inverse of -2. What does that give me? Tangent inverse is defined as negative in quadrant 4. Am I still in radians? I'm still in radians. So tangent inverse, and I've been given a value of -2. So it gives me my starting place as -1.1071. So x is -1.1071. And we know again that tangent is periodic over pi. So this is where n is any integer, all possible solutions right there. Now let's consider just the solutions within my given interval. Well, if n is 0, I've got pi fourth and -1.1071. If n is 1, then I'm going to add pi to each of those. 1 pi fourth plus 4 pi fourths is 5 pi fourths. If I start with this value and I add pi, I get to 2.03444. 2.03444, 1, 2, 3, 4. Let's go again. Let's go to n is 2. Well, I'm going to add pi again if n is 2, because any integer right there, I already added pi once. I'm going to add pi again. Well, plus another 4 pi fourth puts me at 9 pi fourths. That's outside my interval. 0 to 2 pi, that would be 8 pi fourths. That's outside my interval. If I start with this 2.03 number and add pi again, that's still within my interval because my 2 pi is approximately 6.28. So 5.1760 is within my interval. Notice this negative value is not inside my interval. Do I need to add pi again? Do I need to go to n equals 3? Well, no, this one's already out. And if I add 3.14 to this, it's going to be at 8 radians, and that's outside my interval 0 to 2 pi. So my solution set that sits inside my interval are those 3 angles. Make sure in my math lab that you pay attention to how many decimal places it wants those approximations rounded to. What if you have a quadratic function but it's not factorable? Well, let's see what we do then. Example 4. Now is when we're going to pull out that quadratic formula that we were talking about earlier. Okay, so this is kind of a mess because if I move this 1 over, this suddenly is not, these are not pretty factors, and I can't set them equal to 0 since it's not equal to 0. So I have to do some cleaning up of this before I can proceed. Let's go ahead and distribute cosine x and move the 1 over. That gives me cosine square x plus 2 cosine x minus 1 equals 0. Well, this is not factorable because there's no way, since the signs have to be different in my factors, that I'm going to factor this and end up with a plus 2 in the middle, which means my solution set is either imaginary, in which there are no solutions, no real solutions, or it is irrational, which is what I'm betting on. So we're going to use quadratic formula to solve for cosine x, where I have negative b, so that's negative 2 plus or minus square root of b squared minus 4 times a times c all over 2a. That gives me a negative 2 plus or minus square root of 4 plus 4 is 8 over 2, and sure enough, I have two irrational solutions. So when I simplify that square root 8, I have 2 square roots 2, and that simplifies to be negative 1 plus or minus square root 2. So my two solutions for cosine x are a negative 1 plus square root 2 and a negative 1 minus square root 2. And I need to plug both of those into my calculator to get an approximation. All right, so cosine x here is going to be approximately, if I plug this into my calculator to 4 decimal places, I get 0.4142. For negative 1 minus square root 2, cosine x comes out to be approximately a negative 2.4142. And you know what? My cosine function values are restricted to negative 1 to 1, so that is outside my domain. That does not exist. I only have to be concerned about this. So next step, I plug in cosine inverse of 0.4142, and I consider whether or not I need to be in degrees or radians. We're doing radians here. And I'm doing all solutions. It just says write the solution set. It doesn't give me an interval. So I'm doing all solutions, and I'm using radians. So my radian angle measure, whose cosine function value is 0.4142, is going to be a positive 1.1437. Now, let's think about this to make sure that we get all possible solutions. 1.1437, cosine inverse is restricted to quadrants 1 and 2. It's positive in quadrant 1. So this is 1.1437 radians. Now, this cosine function value is positive in quadrant 1. It's also positive in quadrant 2. And the value in quadrant 2 is going to be pi minus this many radians. So let's look that one up. If we do pi minus 1.1437, that puts us in quadrant 2 at 1.9979. 1.9979. Those are the two locations on my unit circle. Oh, you know what, guys? I just did this totally wrong, and there's no one here to stop me. This is why I hate teaching to a camera instead of teaching students. Is cosine positive over here? It absolutely is not. Cosine is negative over here. That's not where my second set of solutions come from. My second set of solutions come from quadrant 4 because cosine is also positive in quadrant 4. So I've got my first set of solutions every time I rotate around and land back there because cosine is periodic over 2 pi. So I've got 1.1437 plus 2 pi n. That's my first set of solutions. Then I've got a second set of solutions down here because cosine is positive in quadrants 1 and 4. I apologize, guys. Cosine is positive in quadrants 1 and 4. So I'm 1.1437 radians above the positive x-axis here, and then I'm that far below the positive x-axis here. So I'm going to start at 2 pi and subtract that. So if I do 2 pi, and I subtract my 1.1437 radians, I am at 5.1395. 5.1395. This radian value is the angle in quadrant 4, where if I rotate and keep coming back here, I have another set of solutions. So 5.1395 plus 2 pi n. And both of these where n is any integer. That is my all solutions set. And I'm not asked to do an interval, so we're going to stop there. Okay, because this is another video that's getting super long, I'm just going to give you the solution to the next one. You would set it up and have to solve and use the quadratic formula just like we did before. The solution set you get is all values of x 1.2768 plus pi n, where n is any integer. Why is it just one solution and a periodic over pi n? Well, we're dealing with cotangent instead of cosine. Okay, let's look at example 5. In example 5, we are solving using trig identities. So now we're not able just to use the algebraic processes that we are comfortable with. Now we're going to be looking back at our identity sheets to see what we can use to solve. Something to remember, you are going to need a single function. So you're going to want to move toward everything in terms of sine or everything in terms of cosine, or in this situation, everything either in terms of cotangent or cosecant, but you can't have those two separate functions there to solve for very well. Something else to remember, when you square both sides to solve, and this is from algebra, when you square both sides to solve, you may create an extraneous solution, so you have to check solutions, because the process of squaring to solve may have created an extraneous, you may have extraneous solutions. Okay, so we're told, we're given a hint, we're going to solve this trig equation by squaring. Well, why would we solve it by squaring? We would solve it by squaring because we need to get to a single function, and I can connect cotangent to cosecant through one of my Pythagorean identities. The Pythagorean identity that I want to use says that cosecant squared x equals 1 plus cotangent square x. Well, I've got cotangent on one side and I've got cosecant on the other, so I can do a substitution if I have everything squared. So let's square both sides of my function. When I square both sides of my function, the right is cosecant square x. I'm going to be able to do that substitution. The left side of my function, I square that binomial. I get cotangent square x, 2 times this product, so minus 2 square root 3 cotangent x, and then square this term becomes plus 3. All right, there's that substitution so that I can get it just in terms of cotangent. This cosecant square x is the same thing as 1 plus cotangent square x. So I'm going to do that substitution. Write down, bring everything down on the left side. And then I'm going to try to start solving. Well, I'm going to start by thinking about setting it to 0. If I think about setting it to 0, I would subtract cotangent square x. When I do that, those cotangent squares add to 0 and they're gone. It's not quadratic. So instead of setting it to 0, I'm going to keep this cotangent statement on the left. negative 2 square root 3 cotangent x, and I'm going to subtract 3 from both sides to move the constant across. So I have negative 2 square root 3 cotangent x equals negative 2. Now I'm going to divide out this coefficient so that I get cotangent x is equal to, and that simplifies to be 1 over square root 3, which is the same thing as square root 3 over 3. So I'm looking for cotangent where cotangent x is square root 3 over 3. Cotangent is periodic over pi. So I'm going to have a single solution set to start with. Where is cotangent function value? At what angle x is my cotangent function value? Is it equal to square root 3 over 3? Well, that happens at pi third. And I know I'm in radians because my interval is in radians. That happens at pi third. So this is going to happen at pi third plus pi n for every integer n. That's my all solution set. That's where it's going to be true. So these are the values I'm going to need to check. Remember, we have to check. Well, from 0 to 2 pi. After I get to that limit 0 to 2 pi, I can stop checking. But I need to check all of my values from 0 to 2 pi. So where n equals 0, I've got pi third. If this works, when I plug it into my original equation, it will be true. So let's check that. Where n equals 0, I've got pi third. So that would be cotangent at pi third minus square root 3 should be cosecant at pi third. Well, look at your unit circle. Cotangent pi third, we picked it because cotangent at pi third is square root 3 over 3. Minus square root 3. I'm going to make a common denominator here to make my life easier. To make a denominator of 3, that would be minus 3 square roots 3 over 3 equals cosecant at pi third. Well, cosecant is the reciprocal of sine. So that is going to be 2 over square root 3, which is the same thing as 2 square root 3 over 3. So let's simplify. Square root 3 minus 3 square root 3 is a negative 2 square root 3. Oh, that's a problem. That's not equal. This one's negative, this one's positive, so that's extraneous. That one doesn't work. Well, where's the next place that I have a cotangent function value of square root 3 over 3? Well, I add pi to pi third. When I add pi to pi third, I get 4 pi thirds. So let's check that. Where n equals 1, I would have 4 pi thirds. Let's check 4 pi thirds. Now, if I go to n equals 2, if I kept going, I would have 7 pi thirds. 7 pi thirds is beyond my interval. It's outside interval. It's outside the interval. So I can stop. This is the last one I need to check. Okay, cotangent of 4 pi thirds minus square root 3 equals cosecant 4 pi thirds. We already said this one is extraneous. We want to know if this one's valid or not. Cotangent 4 pi thirds is square root 3 over 3, and then this is going to be minus 3 square root 3 over 3, and that needs to equal the cosecant at 4 pi thirds. Cosecant at 4 pi thirds is a negative square root 3 over, or negative 2 over square root 3, which becomes a negative 2 square root 3 over 3. There we go. Negative 2 square root 3 over 3 equals negative 2 square root 3 over 3. That's a valid solution. So the only angle for which this equation is true is 4 pi thirds. That is the only angle within that interval. Only angle within that interval. Okay, again, because this gets super long, I do not do all of them in my class lecture, so I'm just going to give you the solution for this next one on the page. We would have skipped it in class. The solution set ends up being 11 pi 6 if you want to try to work through that, or watch the My Math Lab video to see how they work you through it. 11 pi 6 is that solution set. Okay, when I am solving a trig equation, here's the steps all in one place. Decide whether the equation is linear or quadratic, because that helps you determine which solution method you're going to use. If there's just one trig function present, you're good. You can just solve the equation for that function. But if there's more than one trig function, you need to rearrange the equation so that one side equals 0 and try to factor. Once you've factored, you set each factor equal to 0 to solve. If it's quadratic in form but not factorable, we're going to use the quadratic formula. Don't forget to check your solutions. Try using identities to change the form of the equation, and it may help to square each side first. If you square, make sure you check for extraneous solutions. Okay. Example 6, describing a musical tone from a graph. This is a time issue again. We have an equation graphed here. The first thing that I want you to notice is that we have more than one cycle that we're working through. We're told that the frequency in hertz is what we're looking for. We're given y equals p in pounds per square foot from a pure tone at time x in t seconds. My frequency is cycles per second. Cycles per second. According to the graph, how many cycles are we going through? So back to there, that's 1. Back to here, that's 2, 3, and then that's 4. So we've got 4 cycles. And how long? Well, my time right here, my time is 0.0182 seconds. And if I do that division, 4 divided by that number of seconds, I find out that my frequency is 220 hertz. Time. The time is the number of seconds per cycle. So I'm going to stack it the other way. And t is 0.00455 seconds. That is the period.